I'll repeat. He's a student president of the ASHRAE Falcon chapter, student branch of Manipal University in Dubai. He's currently in his 4th year of his BE Mechanical Engineering program. He is specializing in HVACR and is working on his final year project with the title Solar Liquid Desiccant Air Conditioning System, which is sponsored by ASHRAE. Student, please come forward.
A very good morning to all you wonderful people. Today I will be presenting my paper on solar liquid desiccant air conditioning system. I'm glad that this project is approved and sponsored by ASHRAE, and it is also my final year project. Let me now talk about the current energy situation in the world. At present, most of the energy in the world is generated by fossil fuels such as oil reserves, natural gas, coal, etc. The problem with these fossil fuels is that they are depleting rapidly, and generating energy from these fuels leads to the emission of gases that causes global warming. Now focusing on the energy use in the UAE. More than 60% of the power produced is consumed by HVAC systems. The monthly load increases during summer and decreases during winter, as shown in the graph. Also, we can observe that the demand is increasing every year. What are the reasons? Now let's find out the reasons for the increase in demand. Main reasons are economic growth, population growth, and the tourism. This shows that the economic growth, which is growing, which has resulted in increase of power demand over these years. To solve the energy crisis, here are some of the suggestions. Firstly, you can either generate more power or make power generation more efficient. Secondly, sustainability of energy. Third, using passive cooling devices. Lastly, having more share of renewable energy. The last suggestion has been met here. Middle East being blessed with abundant solar radiation and long duration of sunlight. And this is why we are using solar cooling. The aspects of solar cooling are: it helps in saving primary consumption, helps reduce the peak electricity power demand, doesn't emit greenhouse gases, so no ozone layer depletion. Here you can see the potential of solar cooling in the regions around the equator. The solar radiation is around 8 kilowatt hour per meter square per day. Thus, to make use of the solar energy potential in this region, we have developed the solar liquid desiccant air conditioning system. The solar liquid desiccant air conditioning system consists of vapor compression and a liquid desiccant cycle integrated with a solar collector. These systems have ability to provide required humidity and temperature level for human comfort while reducing the energy requirement. For those who don't know about desiccant, let me explain it. Desiccants are materials that can absorb moisture from air and can help in reducing the humidity around us. They do not emit any greenhouse gases, hence they are very eco-friendly. The desiccant which we have used in our system is calcium chloride, and we have used it because it is non-toxic and cost-effective. Solar liquid desiccant air conditioning system consists of an absorber, a two-stage solar regenerator, a heat exchanger, a condenser, a compressor, an expansion valve, a boiler, a separator, a solar collector, and a three-way valve. Here is a 2D representation of our system. You can see each and every component placed in order. But it looks a little complicated in the first side, I know. To avoid confusion, here is a 3D view, which is much more clear. you can see all the components placed in order. But in order to understand this system clearly, we'll have to see the system step by step from each cycle. And here we start with the vapor compression cycle. This is a normal vapor compression system. It consists of evaporator, compressor, condenser, and an expansion valve, and also a refrigerant flowing through it. The refrigerant which we are going to use is R134A. The modification what we have done to this normal VCS is we have used an absorber instead of the evaporator. This is the absorber. It consists of a honeycomb mesh which is placed in between two panels, where the top panel consists of an evaporator coil, so the refrigerant can flow through it. And the strong liquid desiccant solution is made to flow through the top through this honeycomb mesh, and it will stay there. And the room air will be blown from using the fan from the room into this honeycomb structure or honeycomb mesh, and the moisture from the room air will be absorbed by the liquid desiccant because of the pressure difference between them. Once the moisture is absorbed and the temperature is reduced by the evaporator coil, the conditioned air will be given out. Hence, we can get the conditioned air at the required temperature. Yes. And as it absorbs moisture, the solution will change into a weak liquid desiccant solution. But we cannot have a continuous supply of a fresh liquid desiccant solution since it is not economical. So we have to regenerate this weak liquid desiccant solution again. I hope you understand what is the difference between weak liquid desiccant and strong liquid desiccant. In strong liquid desiccant, the concentration of the desiccant is more, while in weak liquid desiccant, due to the absorption of moisture, the level of water content will be more and it will become a weak desiccant. So now what our problem is, we have to regenerate the solution again so that it becomes strong solution and we can use it again. So here is this complete solar liquid desiccant air conditioning system which we'll use during the daytime. Here the green line represents the strong liquid desiccant solution, the red line the weak liquid desiccant solution, the blue line the refrigerant. As you can see, the weak liquid desiccant solution will first flow through the heat exchanger, where it will get heated up slightly, and then it further moves to the condenser. From the condenser it will further get heated up. After condenser, it will flow through the three-way valve, where the valve will be open and it will go to the solar collector. This is an evacuated tube solar collector which will heat the liquid desiccant at around 130 degrees Celsius. The liquid desiccant will, after getting heated up, will flow to the separator. This is the first stage of the regeneration part. Here, the liquid desiccant, here the separation will take place and the vapor will be separated from the liquid. And the separated liquid desiccant, with having the same temperature, will move to the second stage of regeneration. The second stage regenerator is similar to the absorber, consisting the same honeycomb mesh, and the weak liquid desiccant is made to flow over this mesh, the same like we had done before. The outside air is blown with the help of a fan through this honeycomb mesh, and what happens here is, here the liquid desiccant will lose moisture to the outside air and the air will be rejected to the surrounding. This happens because of the pressure difference. Here the pressure of the liquid desiccant will be more than the outside air, so it will directly give out the moisture. So now what happens? The liquid content will reduce in the liquid desiccant, the concentration of desiccant will increase, and we will get a strong liquid desiccant solution. This strong liquid desiccant solution is then again pumped back to the heat exchanger, where it will reject some heat to the weak liquid desiccant solution, and then it is further moved to the absorber, and the process will repeat again. In this way the cycle repeats. So that's the solar liquid desiccant air conditioning system during the daytime. During night, we cannot use the solar collector. So what we do is we close the three-way valve, and the weak liquid desiccant solution is directly fed to the second stage regenerator. Here the temperature what we get from the heat exchanger and the condenser is enough, because the cooling load in the night time is not very high. So it is enough to get the properties back, and we can get the solar liquid desiccant, uh, strong liquid desiccant solution back. This is the working principle of solar liquid desiccant air conditioning system. I have shown this in the form of state points. It's a graph between pressure and temperature and concentration lines. You can find how the temperature, the pressure varies with the processes taking place here. First we'll begin with the process absorption, process A to B. You can see here the temperature is increasing. No, the pressure is increasing, the temperature is slightly increasing. This happens during the process A to B, which takes place here. Next is the heat gain in solution heat exchanger, B to C. Here you can see the pressure as well as the temperature are increasing. Why it happens? Because the temperature increases because of the heat gain, and the gas expands, or the liquid desiccant expands, and the pressure also increases. Next again the heat gain in condenser takes place here, and this is the process C to D. Again we have the pressure increase as well as the temperature increase. Next it is the solar collector, where again heating takes place. Again we have pressure and temperature increase. Once it is fed to the regenerator in the first stage, it will lose the liquid content or the vapor content, and the pressure will decrease suddenly, as you can see here from E to F, while the temperature will almost similar to what it was. Then when it further moves to the second stage, there's again, because it loses moisture to the air, it will again lose the pressure, and the temperature is just similar to what it was. Next, when it is pumped back to the heat exchanger, it will lose heat to the weak liquid desiccant solution, as I said earlier. So the temperature and the pressure will reduce. Next process is heat lost in the evaporator, which is here where the heating coil is placed, and the temperature as well as the pressure will reduce. In this way the whole cycle will keep repeating. Here I conclude that the COP, using this system, the COP of conventional VCS can be increased by 30% by incorporating the solar liquid desiccant air conditioning system. Also, the cooling effort required by solar liquid desiccant air conditioning system is 30.5% lower than the conventional VCS for the conditioning of the same mass flow rate of air. This shows that the solar liquid desiccant air conditioning system is techno-economically viable for the applications like comfort air conditioning, clean rooms, pharmaceuticals, and other industrial air conditioning systems. I hope you understood the system, how it works. If any questions, please ask me. Thank you.
Compared to the conventional vapor compression system, you are not actually doing away with the compressor. Here also the compressor is there.
we are using actually. We are incorporating the BCS cycle.
Yeah.
And we are just adding the solar collector to it and also the liquid desiccant system, which will reduce the power load, which will, yeah. Well, I didn't research about that, but I just know how solar liquid desiccant works. Yes, but I don't think like commercially it is that. No, but even if we can make 30%, that will be really good here because we don't even have solar air conditioning system in most of the places. So if we can make this and at least try to reduce even 30%, that will be very helpful for us. And somehow we can reduce it. Yes. Yes. No, we didn't start yet, but we will do it because it's my project and I have to do it. So, yes, this is just the beginning. Like we didn't actually go into depth. The production didn't start yet. Yes, so but we are still trying to make it more compact, more smaller, and use less components or try to use cheaper components and make it like. We are making a working model. Yes. Yes. Yes, I just have one arrow and it shows the flow. Yeah. Yes. Yes. See, once it gets heated from the solar collector, there will be a formation of vapors. So vapors but we need liquid desiccant in the liquid form. So what we do is we separate the vapors from it and the liquid we use it. So the separator it will separate the vapors from the liquid. Yes. To the air, yes. Not the water vapor. The liquid content will reduce in the liquid desiccant solution. We have a solution of. No, it will lose the water content. It is in the liquid form when it comes to the regenerator, that second stage. And it's a solution of water and calcium chloride. 30% calcium chloride, 70% solution. I mean water. So when it comes here, I'm sorry. Water vapor is separated, yeah. But that is not enough. As you can see the graph, you can understand better. This is the graph. We get the pressure, we lose pressure up to here. But our initial concentration line was this one. We need the concentration at this level. This might be around 35%. And this is around 40%. This is 30%. We need 30% back. Right. I think it's the other way around. This was 40. Water level is more here. So it's water level is 80%, 75%. Yeah. Or in two stages. The absorber is placed in the room and the regenerator is placed in the outside surrounding. So the outside air is taken and the water content will be lost because of the pressure difference between the liquid desiccant and the outside air. And in this way we can reject the air itself in the surrounding air. Because it is placed outside, so it will go out in the environment. But I wanted to show the concentration, so that's why I used this diagram. I also have the other diagrams, but not right now. We are working on that.
So this liquid has the affinity for the water vapor.
Yes.
Right? But how you can use the water vapor to the atmosphere?
Yes, I told that also. Because of the pressure difference. Yes, it will lose. I don't know proper theoretical answer, but I have studied it will lose the water vapor, only the water contamination.
There is the expansion valve in the system.
Right?
Expansion valve.
It's here.
Yeah.
She is a master's student in the Mechanical Engineering Department in the Petroleum Institute. She obtained 2 bachelor degrees from China University of Petroleum, one in Industrial Design and another in English Literature. She had been involved in the research of design of secondary seal valve, design of dangerous gas detection and imaging device, and the research on magnetic technology for separating gas and impurity. Now she has been working on the research of the, I think it's lithium bromide, it's weird saying LIBR, / water absorption using microchannel technology under the supervision of Dr. Ibrahim and Dr. Muhammad. Please, Ms. Liam.
Good morning, everyone. My name is Yunshan Liu. I'm a master's student from Mechanical Engineering Department in Petroleum Institute. The topic of my presentation is modeling of lithium bromide water absorption in a single microchannel, which is supervised by my advisor, Dr. Abraham. First, I will give a brief introduction to the absorption refrigeration system and also the macrochannel technology. Also, how microchannel technology is applied to absorption refrigeration system to increase the performance. Later, the numerical simulation using COMSOL will be presented for a single microchannel absorber. Then the conclusion and future plan. As we know that combined heat and power generation is based on heat-driven technologies. Therefore, heat exchangers significantly affect the cost and the efficiency. This effect is more pronounced in hot climates. With the increase of the temperature, the efficiency of the machinery will drop, and also heat rejection is very complicated. As the temperature in Middle East is very high, so cooling is more in demand compared with heating. Absorption refrigeration system is a very old system which has been already applied practically. This is a general schematic of absorption refrigeration system. The working principle is like this. Take lithium bromide water as a working fluid pair. Then we can see that from the evaporator, the water gets vaporized and then sent to the absorber, where the strong lithium bromide solution is. And then the water vapor gets absorbed in the absorber, became the weak solution. The weak solution is then pumped to the generator, where waste heat, where heat can be utilized to vaporize the water again and send to the condenser to recycle for the recycling to the evaporator. The strong solution from the generator will again send back to the absorber for later absorption use. The advantages of absorption refrigeration system, as we can see, the generator needs heat input, and this heat input can be any source of heat. Especially, we can use the waste heat generated from industries. There is no moving parts except the solution pumps in the absorption refrigeration system. And also because of its application, it has become a proven technology. As we have mentioned before, in hot climate, cooling is more in demand. Thus, in this way, waste heat utilization can be realized through the absorption refrigeration system. But the disadvantage is the coefficient of the performance of the whole cycle is relatively low. Single stage cycle is about 0.5. One of the application example we can see from the graph here, the heat generated from the exhaust outlet can be reused for the generator, and then the cooling air generated from the evaporator can be reused for the turbine to increase the efficiency, the performance. And this is the statistic data. From here we can see the hotter the climate is, the more efficient this absorption refrigeration system is. Microchannel technology is microscale based. Instead of using large tubes like the conventional absorbers, we are using microscaled channels for the heat exchangers. The advantages can be the size can be reduced to 1/10, and because of its reduction in weight and volume, it also saves energy, saves material, and also it's easier to operate and maintain. It's easier to control, and it has better performance. Because of its waste heat utilization and improved performance compared to conventional technologies, the conventional heat exchangers, there will be substantial reduction in carbon footprint. As an absorber is a combined heat and mass exchanger, it is one of the critical components of the absorption refrigeration system. For the design of the absorber, we desire that it's desirable that it can have low pressure drop for both the liquid and the vapor. And we also want it to be cost effective, which can be realized by achieving high heat and mass performance and a large surface contact area. Two main categories of absorbers are listed here. One is falling film, another is bubble absorption. The key difference between these two models are whether the vapor getting absorbed in the absorber is in bulk phase or in bubble phase. If it is in bulk phase, then it is falling film absorption. If the vapor getting absorbed is in bubble phase, it is a bubble absorption. This is a schematic of the falling film absorber. The disadvantage of this is because of its gravity and the design, incomplete wetting and also flooding will occur. Also, because we want to create the falling film, the liquid distributor is needed. Bubble absorption. The disadvantage is that large pressure drop will occur in both vapor and liquid phases. And also, backflow of liquid will lead to smaller coolant solution heat transfer area compared to falling film absorption. That's why we are starting microchannel technology and trying to utilize to apply it into the absorption. This is the photograph from our lab, the absorber design. The first is the side view. The first one is this one is the visualization glass for the visualization, and then the absorber base, then the gasket, and the bottom cover. Also, we have another channel in the backward of the absorber for the coolant to flow countercurrently to remove the heat generated during the absorption process. The photo on the right is a photo taken from a literature. The first one is a cross-ribbed channel. Second is a 45-degree angled cross-ribbed channel. The third one is a streamwise finned channel. The microchannel shown on the right is actually integrated. In our case, we are using separately. Integrated is more efficient but more difficult in manufacturing. Here it comes to my numerical simulation results. I'm using 2D numerical model in this stage. Also, the application mode is convection and diffusion because the water vapor getting absorbed in lithium bromide solution is total physical. There is no chemical reaction. The computation method here I choose Lagrange quadratic. These are the constants I have set during the simulation. The diffusivity of water vapor in air and also the diffusivity of water vapor in lithium bromide solution. Here the lithium bromide solution, the concentration of it is set to be 30% mass concentration. And the velocity of gas and velocity of lithium bromide solution is set, it's changeable. The initial concentration of water vapor in air, initial concentration of water vapor in lithium bromide solution is also set for this simulation. This is the geometry modeling. As you have seen before, the microchannel in our lab at this stage is Y-shaped microchannel, Y conjunction. Here is the lithium bromide solution inlet. Here is the water vapor inlet. These are the walls and that's the outlet. The subdomain and the boundary settings are set separately from the lithium bromide solution side and from the water vapor side. The width is this one, and the length here I just mentioned the mixing area from here to the end, the length of the mixing area. These are the general the results for the concentration of water vapor absorbed in this mixing area of the microchannel. The first stage of my simulation, I set the velocity of water vapor and the velocity of lithium bromide to be the same to see the general performance. From the results, we can see that with the increase of the velocity of water vapor and the lithium bromide solution, the fully absorption area region decreased significantly. Here we can see the velocity change is very small, ranging from 0.1 to 0.6. When the velocity increases to 0.5, almost no fully absorption area can be observed. Next stage I cite from the literature. I learned that the velocity of solution does not affect the absorption performance as much as the velocity of gas. So I fixed the value of the velocity of the solution side velocity. Then I increase the velocity of the water vapor. U denotes the velocity of water vapor. V denotes the velocity of lithium bromide solution. Here, after citing the velocity of lithium bromide solution to be 0.1 meter per second, and increase the velocity of water vapor, it can be seen that the same trend. With the increase of the velocity, the decrease trend can be visualized from here, can be seen from here. Also, starting from the 0.5 meter per second, nearly no Foley absorption can be observed from these results. But by comparing this photo with the previous one, we can see that with the same velocity of water vapor, the change of the solution side velocity does not affect the performance so much. These are the results I have gained so far. Okay, then I changed the matrix computation methodology to non-symmetrical. The results began to show some difference. The same trend was observed, but compared to the previous one, we can see that larger Foley absorption area was observed. The same result after fixing the velocity of water vapor, after fixing the velocity of lithium bromide solution to be 0.1 meter per second, same trend was observed, increasing the velocity of water vapor. Foley absorption area decreases, but not as much as we are using the previous model. So there is some difference. Then I want to try some higher velocities for different measurement, for different range measurement. So I increase the velocity of water vapor from 1 to 5. Here we can see the same trend was observed, and the Foley absorption area decreases. Also, the place where it starts to where the Foley absorption starts came to be nearer the end of the microchannel area. These are the discussion, like before refining the mesh and before changing it to non-symmetrical computation method. Here I also want to mention one thing. Like from previous symmetrical computation, we can see it is even. Here, it has some angle. This is the inlet for the water vapor. So here, the concentration of water vapor getting absorbed should be larger compared to the area which is nearer to the lithium bromide solution inlet. So I think non-symmetrical computation methodology is more acceptable and more satisfactory compared to the symmetrical. So the discussion. Foley absorption region decreases significantly with the velocity increase of water vapor, but no apparent changes was observed with the increase of the velocity of lithium bromide solution. Also, starting from the velocity of 0.5, no Foley absorption, almost no Foley absorption was observed in the mixing area. After refining the mesh, still the same trend was observed. Foley absorption area decreases significantly with the increase of the water vapor and the lithium bromide solution, but different absorption performance, as we can see. Compared to the symmetrical computation, non-symmetrical computation gives less Foley absorption area compared to the symmetrical. under the same settings. Also, it was observed that Fourier absorption region decreases significantly after the velocity increased to 1 meter per second from 1 meter per second on. The future work, the conclusion is that lower velocity can be suggested for better absorption performance. As we can see from the previous one, these are the Foley absorption area. This means we don't need the length of the macro channel to be so long. We can decrease the length of the macro channel for lower velocity. Also, as seen from this photo, after you reaches 5 meter per second, almost no Foley absorption area was observed. That means we can increase the length of the macro channel. And my future work will be simulation results will be compared later with the experiments using the same macro channel geometry like as what I have shown in the previous photograph. Modeling of different junctions, I can use Y junction and T junction of the macro channel. Different junction, different dimensions of the micro channels will be conducted to compare the absorption performance. Also, heat transfer performance will be involved in the future simulation because in this simulation, only mass transfer performance, that is the concentration of water vapor getting absorbed in the microchannel, is involved in this simulation. Okay, thank you. Do you have any questions?
See, when you're talking about the microchannel,
Yes.
so the absorption is better. The absorption
Yes.
of the water vapor is better.
Yeah.
But when you are talking the dimensions in the micro quantities, the same amount of solution would flow through the microchannel. So you'll be requiring more number of channels.
Yes, we are increasing the channels in later. Here is
Same quantity of solution.
yes.
Otherwise, which will be flowing in the system. So when you are talking about the channels in the micro dimensions, so what will be the total number of channels that will be required? So that will be comparatively very large, no?
Yeah, now we are just, on the preliminary stage of this study. So the study now I'm conducting is just based on single channel. Later I will increase the channel because you cannot just put this into practical application. This won't be so much effective. We will increase the macro channels, the number of micro channels. Also, we will figure out what's the appropriate value used in practical application.
So for this to have a practical application, then we'll be having so many number of channels
Yes.
to be welded together, to be formed,
Sorry, to be what?
to be constructed actually. So
Yes.
many channels to be coupled together and should be constructed.
Yes, it's like batteries of micro channels.
So one more question is actually you are talking about the velocity of water, velocity
Yes.
of water vapor.
Yes.
So velocity of water vapor, if it is increasing, the absorption capacity is decreasing.
Yes.
So that means lower velocity.
Lower velocity was suggested.
Yes. So for that to happen, then it will take longer time for the absorption to take place. No? So how to actually carry out the process then? Very low velocity.
Yes.
Then how to carry through the process actually? So it will be taking place very slowly, no? And the velocity is reduced for the absorption to take place.
Yes, what you are talking is correct. But I'm also mentioned like now you can see the velocities are smaller, 0.5 to 0.1 to 0.5. I have also mentioned we can increase the velocity from 1 meter per second to 5, based on this macro channel. Later you can increase the length of the micro channel. The larger velocity can be applied. Thank
You
you.
have not shown any mathematical modeling of this.
It has the COMSOL. It has the mathematical. You have to input the equations inside to do the simulation. Thank you.
Okay, start 15. on the other side of this, what is the scale? What does indicate absorption and non-absorption? Is it the gray or the red?
You mean the scale? From here to here, it can be seen. There is 0. This is the largest concentration of a water vapor getting absorbed in the solution.
So what is absorption, fully absorbed?
This one, the red area.
What is the, I mentioned the size of the channel was
2.7 in wide, millimeter.
Okay. What's the height of the channel?
It's 0, let me see. 0.7 something, 0.7 millimeter. Height of the microchannel. Actually, it's just like a board, very thin one. You can see from here. This one. You can see from here. This is actually a macro channel. It's just like a very thin board. Thank you.
For the modeling, it's better, since you're doing a parametric study, it's better to show, a matrix. What are you going to do? Changing the velocity,
Yes.
the range, whatever. So your audience will follow up with you on their later slides.
Yes.
And as Dr. Baer mentioned, we have to make it clear to the audience what's the, in terms of color, in your modeling, what's absorption, what's not absorbed, and the difference.
Yeah, I will make the according revisement later. Thank you.
Thank you, Ms. Liu. Next, we're going to have the last presentation by Syed Omer Ashraf, who is a student of mechanical engineering at NED University of Engineering and Technology in Pakistan. With interest in the HVAC field, he is presently serving as Vice President of ASHRAE NED Student Chapter. He has worked under the guidance of his seniors and in collaboration with his team for the promotion of student activities.
I would like to apologize, but due to the lack of time, we only got 12 minutes. So are you sure you would?
I'll find
Because I think she took.
Good morning, everybody. Half of the thing has been done by another lady, because my topic of presentation today is solar absorption air conditioning, which resembles her topic. One thing she forgot to mention is I'm a student of second year mechanical NED, a sophomore, what you call there. So basically, to begin with, the objective of this presentation is to increase the COP of the system by making 2 partition storage tanks. And basically, the location of this system is basically Karachi, Pakistan, with average solar energy of 15 megajoule per meter square, meaning that the total solar radiation per the areas is 15 megajoule per meter square. Now, basically, we should know before beginning the presentation that what is actually solar absorption. Solar air conditioning refers to any process that uses solar air energy for air conditioning. And in solar absorption air conditioning, we have systems. We have solar thermal collectors that collect the thermal energy from the sun and then drive the thermally driven chillers. Very simple. This is a schematic diagram of the system. Here we have a collector, hot water storage tank, auxiliary heater, generator, condenser, we have the evaporator, absorber, and the cooling tower, and the chill water storage and the cooling space. Now, we'll break the system into step-by-step explanation. But the first step is the collectors. Basically here, the collectors which we have proposed to use are the flat plate collectors. You can feature the double glazing and the insulation so that you can withstand the temperatures up to dealing with 93 degrees centigrade or 200 degrees Fahrenheit. The working fluid which we have used here is basically lithium bromide solution, And if you see the book by P.J. Wilbur and D.S. Word, they have proved in their studies that using of COP, using lithium bromide as the working fluid, it has better efficiency, it has better COP than other working fluid models in solar absorption systems. The first process. Initially, from the sun, the collectors receive energy, solar energy. Then, after that, the hot water is transported to the storage tank where it evaporates water vapor from the solution of lithium bromide. Now, that water vapor goes into the condenser. If you are following the diagram here, from here, the water vapor gets evaporated and goes into the condenser. In the condenser, the water vapor which has been produced is now cooled with the help of cooling tower water. And then from the condenser, the cooled water now goes to the evaporator, where it is being evaporated at low pressure. You see, the pressure here is low. So in order to evaporate, it requires heat energy. This is water and it requires heat energy. So the heat energy is removed from the storage tank here, which in turn is connected with to the cooling space. The space which we need to cool is connected with this storage water tank. Now the water vapor takes heat energy from this storage tank, which turns into a chill water storage tank, as we have mentioned here, because the heat is removed. And then in turn, this chill water storage tank cools the required cooling space. With the help of fan coil, we can ensure proper circulation of air. Then after that, this water vapor, which has been converted from liquid to water vapor, goes into the absorber. Now in the absorber, the strong solution of lithium bromide produced in the generator earlier in our diagram, as you see here, there was a strong solution. In the solution of lithium bromide, the water vapor was boiled off and a concentrated solution of lithium bromide was left here. So it serves as two purposes. It is reused in reheating the incoming weak solution from here, and it then goes into the absorber. And here as we mentioned that water vapor is coming, so it gets absorbed with the strong concentrated solution of lithium bromide. So in other way, we are regenerating the working fluid that was converted earlier as a concentrated fluid. It has now been reconverted into a weak lithium bromide solution. After that, the heat of mixing produced in this process is taken away again by the cooling tower. The cooling tower basically is now serving two purposes. It's taking away heat from the condenser as well as the absorber. You can see the loop here clearly mentioned that the cooling tower is linked with the condenser as well as the absorber. The heat of mixing produced here is taken away from the cooling water in the cooling tower. Now, after that, we have the weak lithium bromide solution, which is produced, as I mentioned earlier, is regenerated into the system. Now the main features of this system are the auxiliary heating. Auxiliary heating means that you are providing heat when there is low sunshine. When the sunshine is low, you are providing heat, and the main function of this auxiliary heating is to maintain the constant temperature, is to provide constant temperature when there is low solar radiation. And the other main feature is partition hot water storage tank. Now, in order to understand it, you can consider partition hot water storage tank as a storage tank with number of segments. Now, in the first mode, for example, which is a normal water storage tank, we have divided into three modes: a normal storage tank, and similarly we have four modes, which is also all the four modes are stratified. But in the third one, In the third mode, we have two normal stratified segments, but one, the first, which is normally the 1/4 of the total storage tank, is not a stratified one. Why? Because when the sunshine is low in the early morning or in the late after evening, when the sun is setting and the sun is rising and sunshine is low, so what we do, we connect, here is the top portion. So we have connected the auxiliary heater in the parallel. So when the sunshine is not coming from here, we are running our auxiliary heater, and then we are heating only the small portion, about 1/4 of the total storage tank. This means we don't have to heat the whole tank in order to keep the system operational. The equation which have been proposed by these researchers in their articles is the basic equation for any collector is this, for a simple collector. Now, the circulation pump, which actually starts the system, basically is operated in an on-off mechanism. When the temperature at the bottom of the storage tank and the collector is low, the system becomes operational, and when the difference is high, the system is non-operational. This mechanism ensures it gives the guarantee that the pump will operate when there is only sufficient solar radiation. The next main thing is the chiller. Now, the chiller, which we have considered here, is a standard 4.7 kilowatt chiller, and with the inlet water temperature of cooling water is 29.5 degrees centigrade. Now we have a standard graph. If we have the chill water outer temperature on the x-axis and the y-axis is the refrigeration capacity of a chiller, keeping in mind that a cooling inlet water temperature is assumed here is considered to be 29.5 degrees centigrade. Now here, as you observe carefully, that our generator temperature is around 88 degrees centigrade, somewhere here, or 85. So, and our required target to obtain the chilled water storage tank is 9 degrees centigrade. That is, we want to achieve that temperature. So, if we intersect the line, so our efficiency around 0.5 or below 0.5. So, this system, the refrigeration capacity is below 5 or 4. It's between somewhere there. So, in kilowatts. So that is why it again proves that the refrigeration capacity which we have considered coincides with our data. And then we have to consider most important thing, the COP of any system, which determines its feasibility and its actual production, whether it can be made or not. So if we again analyze, our chill water outlet temperature is 9 degrees centigrade with our 85 or 88 degree graph of the cooling water inlet temperature, the COP coincides to somewhere around below 0.5. But below 0.5, so we consider this system around 50% efficient. And after that, we have the cooling tower, which we have explained is serving the purpose of two things. It's taking water from the absorber as well as the evaporator, the condenser. The cooling tower space, so it's the capacity of this cooling tower is to 12.7 kilowatts. After that, we have the water tank. Just to have a brief review of this. Now in the water tank, if you consider QU as the heat gain from the collector and the load is LS, the cooling load, or you can say the energy removed. So you can formulate or you can propose n differential equations. If there are n number of nodes, as we consider in our storage tanks there were 3 or 4 in the stratified one. So we can make n number of n differential equations in order to determine the energy balance equation for each section of the tank. So we had 3 sections or 4 sections. So we will be having 4 n differential equations. which will give the energy balance relation at any point in the storage tank. And after that, we go to the results. The results were, first of all, in partition storage tank, the generator temperature, which is normally 88 degrees centigrade, so that the chiller may become operational. So since we have divided our storage tank into segments, this one, only this portion requires heating in the morning. So when the temperature is low, our system becomes operational comparatively earlier. If you were to have considered this mode or this mode, where the whole storage tank first needs to be heated and then the system would become operational. So in our case, we have just heated a small segment. This segment is behaving as a small storage tank. So we can start the system earlier as compared to the normal storage tanks, hot water storage tanks. And the second most important result is that the generator temperature is achieved later and the higher temperature, and moreover, the COP of the partition is also higher. How the COP is higher? Naturally, when you are getting the system operational earlier than the normal one, and you are saving your cost, so you are increasing the efficiency of the system. Moreover, you are getting more heat to be removed from the cooling space, and you are making more heat removed with the same amount of input work. So this increases the efficiency of our cooling, of our system. Then we have the conclusion, and one more thing which I have to mention here is the COP of the lithium bromide solution. As proposed by various in the book DS Word and this, the lithium bromide solution, as reported by DS Word and in their book and DS Word, pages 259 and 268, they have clearly mentioned that if you use lithium bromide as a working fluid in solar absorption systems, it is best because it increases the COP rather than other working fluids. So the conclusion is basically of this presentation is that solar air conditioning is highly beneficial, and it is very efficient system, and it provides greater cooling when there is more sunshine. The most important factor is that when there is high sunshine, you need more cooling. And then when there is low sunshine, you don't have that much cooling. Why freezing your feet and hands? So this system provides cooling as it is needed. When there is more sunshine, we will give more cooling, and when there is low sunshine, less cooling. So similarly, you are saving a lot of energy in this case. You are not wasting any energy. That is basically the main theme of this paper. Moreover, this cost efficiency of this system is much more better than the other one. Why? Because since we have mentioned in the results, we have three benefits to it, that it increases COP, the system starts earlier, and we reach the generator temperature earlier. So basically we are saving money, we are increasing the system efficiency, and we are providing cooling when it is needed, rather than not wasting our cooling. Thank you. Any questions? If you have understood the presentation.
When you say the efficiency, adjusting
Yes.
the COP and the by this change the system.
Yeah.
What is how much the COP is increased?
Yes.
How much the COP increased the previous case and
In this case, yes. You see, normally the solar absorption systems have COP around 0.2 to 0.3. If you are very efficient in the storage tank mode, you can achieve 3.5, not more than that, because there's a lot of waste heat energy involved. So this has increased our COP to around above a 0.4 and below 0.5, somewhere in between. So that is why we are considering that we have increased considerable amount of CO2.
So do you have just drinking water or?
No, it's a theoretical model.
Are you going to do that?
Since this is my sophomore second year, I plan to do it in my final year, and I have started working very early so that I may achieve something at the end of 2 years. Time.
Again, scenario as you said, Pakistan and
Yes, because you see, especially in this country where there is more solar radiation, and it is being wasted. It's just a free source of energy. Even back in home in Pakistan, there's a lot of sunshine in summers, but nobody is utilizing there. And similarly, I happen to observe that here also there are very few solar absorption systems. So we have a very good potential here to use these systems so that we can get rid of these oil dependencies, to just fire the chillers, the diesel fire chillers and the coal and the fossil fuels and pollute the environment.
Coming to the stratified compartments, yes. That means you want to heat it separately.
Yes.
Provide separate heaters for each compartment?
No. You see, the purpose of this compartment is to ensure uniform heating of the storage tank. Basically, this is a special one. These two are the special ones. This is the main theory of our subject. Here,
The different compartments, they are fully insulated?
No, they are not insulated. This is a perforated layer. But this one is insulated, and we can couple with the rest of the storage tank as we need it. If we consider that the sunlight is more, we can open the valve here, and then this whole storage tank behaves as one. But in the morning when the sunshine is low, we can separate it from the rest of the tank and behaves as a small storage tank for the small requirement.
Quantity of hot water only will be ready.
Yes, but because
Only small amount of refrigeration only will be done.
yes, because in the morning we don't require such large amount of refrigeration. There's the temperature outside, the ambient temperature is low. So why should we cool the place when there's no one there in the office? You getting my point? Hope I answered the question. Any more questions?
This is only modeling, right?
Yes.
The heat exchangers, what materials are you using?
Basically, we have used the standard heat exchangers. The copper type is heat exchangers which we have used here. And since we have not gone to the depth and the detail of the production, so it is still yet to be decided that what material would be more efficient here.
I'm sorry, but you're going to have to stop because we're going to have to, sit down and talk. We're going to go to the stairs. Really sorry, okay? Everybody gets ready. Yeah, I'm sorry, I just wanted to say the awards, because tomorrow we have a panel discussion, we also have to have an award for that. So we're just going to have both awards presented tomorrow because we don't have time now. So for this technical presentation, the award will be presented tomorrow, okay? We'll announce the winner tomorrow, alright?
As you all know, being members of it is doing well and good for everyone. It's making or creating a common language to all the engineers everywhere to apply the same standards that they have on heating, refrigeration, and air conditioning. Good. The topic for today is district cooling plants, design and construction. First, a brief about why should I be, the topics that we have is introduction, a definition of district cooling, the difference between district cooling plants and conventional plants. We'll look at major components of district cooling, some optional components that we can look at, which is thermal energy storage. And we'll look at some of the photos that were taken for a district cooling plant during construction. And later on, when we do the tour, you will see the finished product. Inshallah finished, but it's half finished. I'll tell you more later. Okay, why should I be speaking about district cooling? ADC is an EPC contractor in the UAE. We engineer, procure, and construct district cooling plants. We have plants in the UAE. We have under construction in Saudi Arabia, but we have plans to also be in the region, in the MENA region. Originally from Dubai, it's a local company, and we have a great pride in having local knowledge in district cooling, because later on I think the ASHRAE will produce a guide for district cooling, and this guide is partly fed by information that we have in the UAE about district cooling. To talk about contracting first, let me talk about contracting. A lot of you are students. You are at the verge of thinking and planning what you want to do next. Does anyone know what they want to do next after they graduate? Yeah. And then? Okay. And education is good. Anyone thinking about going into contracting? Consultancy, design, operation, maintenance of mechanical equipment, of buildings is also a great place. Whether you might think it's not a great career to be into construction, but let me tell you, every day we wake up and we think, what can we do better in the next project that we do? How can we improve our efficiency of equipment? How can we save ourselves and the client, and in the long run, the building that we are going to construct, a little bit of energy, a little bit of resources that are limited in this country and in every country that we have. This gives you a purpose to your career. This gives you a purpose to be better on the next project that you're doing, to explore new ideas and different ideas, and how to make it a more efficient plant, a more efficient building as such. I spoke about EPC contracting, but to give you the definition of EPC contracting, it is a single point of responsibility in a contract. To be an EPC contractor, you are responsible for the design itself, for the procurement and the efficiency of the equipment, and later on for the construction of that plant. This is different from what you would see normally as a client, consultant, and contractor. A client wants to build something, a consultant or a designer who will design it for him, 100%, fully designed, and then a contractor who comes and constructs only. The difference between those two is a keyword that I told you about, which is responsibility of design and guarantee of performance. And client, consultant, and contractor, the contractor is doing exactly what the consultant has designed, and the designer or consultant is doing exactly what the client has briefed him to design. So there is a vague area of where the responsibility of design or the responsibility of performance of the plant is going to be. Whereas an EPC contractor, you will see that it's a single point that has to guarantee the performance of this plant. Engineering, procurement, and construction. EPC comes from one of the types of contracts that can be signed. There is also another contract called DBO, which is design, build, and operate. There is EPCM, which is EPC plus. Yes, good. I didn't know. And there is the standard design and build, and there is at the bottom of the range, which is only design. Bottom of the range, there is no problem in only contracting and only design, only constructing. Your scope is limited to only constructing the plant and nothing else. Okay. Let's start by defining district cooling. You did not miss much, but think about your future. That's all. What was in the... Okay, still think about your future. District cooling, okay, it's a purpose-built plant that can produce energy or can turn energy from one form into another, be it turning oil, diesel into hot water and steam, or be it turning electricity into chilled water, into ice. All of this is transforming energy. We are doing nothing else but transforming energy, and on the way we pollute the environment a little bit. It is purpose-made, which means that your building is constructed around the equipment that you are selecting. It's not the other way around. Think about a theater or an auditorium where the designer and sometimes the sound engineer will be the one who will dictate the shape of this auditorium, and the architect is the one that will make the shape for it. Here, I think this is one of the greater areas for mechanical engineers and all the engineers, is that you are in the driver's seat in constructing those plants and designing those plants. Why I say this? Because the architect has to listen to the mechanical engineer, what he wants. If I want a pipe here, I want it here. If I want an equipment there, I want it there. And if I want the pump to be vertical, someone has to design that foundation or that building for me to do that job for me. You don't feel that you are on the lower end of engineering, which some of the people in the building services would feel. When an architect tells you that you need to remove your duct from here and put it somewhere else, you need to do that, and that's the end of the story in a building. Again, let's concentrate on district cooling. Let's give you a small idea between district cooling and power generation. It might have started like this, but I don't know. I don't know the history of power generation. But people do not tend to bring power generators or diesel gensets and put them in every building. This is not the way that our modern cities have done it. One way of looking at district cooling is to look at the similarity between that and power generation. what we normally do in cities like this is to have a power plant sitting somewhere, an efficient gas turbine or a oil turbine, oil burning turbine, that will be connected to a grid, which is a transmission line, and this transmission line is giving you power into all the buildings that you have. Similarly, conventional cooling might be inputting chillers on every building that you have there, chillers or any type of cooling that you want, even unitary coolers might work. This way, as you can see, there is a fairly good amount of power that is going into every building. For a conventional cooling system, you will find that there is a large electrical distribution system that is there. There is a standby in every building that you have there. Equipment, because it's a smaller building or a smaller plant, you will find that it's less efficient, it's power consuming more than it should. Operating it will be, every building will have an operation team that will operating that plant, and each of them will have their deficiency in operating those plants. It's a higher maintenance cost because you have in every building an operator who's operating this chilled water plant or mini chilled water plant. And industry cooling will do the same thing that we've done in power generation, which is we have our customers are there. We have a transmission system that is there, similar to the electrical power. It's connected by pipes that can run underground, obviously, and mainly in this area we have insulated pipes that are running under the ground. We largely use steel pipes, normal steel pipes, welded pipes. They have to be welded. Some of the installations that are here have used GRP pipes. HDPE is there. ABS is there. How much do you want to pay? This is all comes down to dollars and cents. And of course, we've got our pride of this presentation. The district cooling plant is sitting there. It is the only one that is connected to power. Let me say that. I mean, we're talking about lighting, we're talking about fan coil units inside the building. It is similar, and it's the same between conventional buildings or a district cooling system that is connected to buildings. But when I'm talking about power here, I don't need any power to generate chilled water or cooling or even heating in the buildings themselves. These are customers that are connected through what we call an ETS station, energy transfer station. Normally there is plate heat exchangers that are sitting there, and that will decouple our buildings from the network. The network can work independently from the height of the building, the hydraulics that you have in the building, or when the building is finished or not finished. Come and look at a situation that we have 3 of those buildings are running, and that 4th building is not running. You need to cap it off somewhere, and cooling has to be given to certain buildings before others. So it can continue and grow. This system can continue and grow. Yeah, that's about it on pipe work. I don't think we need to know more. Differences between them. Okay, similarly to what we spoke about in conventional systems, district cooling plants can be a lower initial investment cost, and some people might argue against this, but take my word for it, it is. How? Don't take it for granted. Always ask questions and always ask why. Yes, why? Take the sum of all your loads. Your building load, your air conditioning load, or your heating load is the same irrespective of what system you are using, whether you are using district cooling or a conventional system. But it comes to the standby that we put on every system. Did you go up on the roof? Some of you went up on the roof? Yes? Yes? In different buildings. But you went up to look at the chillers or to look at the view? No. With fans on them? Yeah, yeah, yeah. Can you imagine the amount of concrete that they put to hold those chillers up there? Throughout the stores and so on. The load of those chillers is there. In every building, you need to have some safety. You need to have some standby. Maintenance of equipment has to be there. Lower initial investment, what I mean by this, if you look at co-ops and cooperatives and collecting all this cooling and putting it in one place, it will definitely be cheaper for you to buy bulk cooling than to buy individual cooling plants. We'll answer it later on different ways. Actually, some of the answer was there. The difficult question that you should have asked is, what if a pipe breaks? That's even more difficult than a plant. A plant, I can answer you now. We have multiple chillers that are sitting in the plant. You design your plant you can go as much as you want in reliability of a plant let me take you to the extreme. You will take your power from 2 different power stations. That's one way of doing it. You will install multiple plants that are connected on the same network. And this way, if you lose some, you still have another. Within the plant itself, you will not serve it from a single machine. And you will not have a single point of failure that will turn off all the plant. Comes to force majeure, yes, anything can happen. If you have a plant that is sitting in Japan, and even nuclear power plants can stop out of force majeure. But you do put in your design a certain resilience in the plant that will go. This building can be fed from this pipe or from the other way around, if you look at it. If you have enough valving on this, and each of those plots or buildings, except this one probably, can be fed from 2 different ways in the pipeway. That's your bad luck. Okay. What will happen? It's not 1, 2 days. A damaged pipe, what will damage the pipe and how much is the damage on the pipe? Normally I would take one risk and only one risk, and I will analyze it. I will not take 2 risks at the same time. Always look at your designs that there is only one failure that happened. If someone will ask you, what if power cuts and the pipe breaks? Thank you very much. I'm not going to analyze this, but what if power breaks? Yes, is a valid question that anyone can ask. What if a pipe breaks? Yes, it is a valid question that anyone can ask. And generally, buried pipes underground they're not easy to break. Steel pipes that are welded, pressure tested, 16 bar or 10 bar, are not the easiest thing to hit them and break them. True. We've done that before. during construction we would have accidents, and these should be you're bound to have failures in the system. Any system can fail. Also, 132 kV cable that is sitting under Salam Street can be hit, and you will have a power outage, and that is an emergency. You can treat your system depending on how critical it is in many ways. I know Dubai Healthcare City in Dubai is being fed from a district cooling plant, and in that plant there was design for multiple failures to happen because they are feeding the hospitals there. At the moment we are executing a contract here on Saliyat, and one of the main items that is being discussed is resilience of the system and reliability of the system, because they are feeding the museums that are being built there, and every single piece of those paintings is going to cost you a fortune. Oh, we went down too fast. Okay. Minimal operation and maintenance, because we don't have multiple sites that we are taking care of. We reduce the electricity consumption compared to conventional system, and this is proven. At the moment, maybe today we can see the power consumption that we have on this Ream plant, but in the range of 0.9 kilowatts per ton, 0.85 is available. We've stretched the limits with Masdar plant that was cancelled at that time to hit the 0.6 or 0.5 kilowatts per ton, which is quite a very good efficiency. You need cooling water, but since you have all the cooling towers in the same place, you don't need to have multiple connections to cooling towers on buildings. Reduces the space that is needed for installation. Definitely, if you have the same equipment in one place, you don't need to waste all this space in different buildings on it. Reliable delivery of chilled water. It is very reliable. You don't need to call on your operator to come to the building. There is people who are dedicated to serve that plant. It's their, let's say, it's their bread and butter to deliver chilled water. There are companies that survive on delivery of chilled water, and this business is there, so it is reliable. Low financial risk if used properly. What I'm talking about here is as the capital that is being spent from a building owner doesn't have to be spent on air conditioning. They can buy the chilled water as and when needed, not because they have a big building they have to spend all the investment on putting chilled water for that building. In terms of efficiency, we can look at a chiller plant efficiency between 1.2, which we consider as an inefficient plant, down to 0.5 or 0.6, which is stretching the limits of equipment that is available these days. Does anyone know what a conventional system would do in terms of kilowatt per ton? What? For the chiller alone? And add the pumps to it? And add the window AC is 2.1. What is a kilowatt per ton? No, what is a kilowatt per ton? Let's define that. Can any of the students give us a definition of the kilowatt per ton? What is a ton of refrigeration? Good. 12,000 BTUs? Okay, good. So it's a kilowatt per kilowatt, but because of ASHRAE, we're accustomed to tons more than anything else in measuring tonnage of chilled water plants or cooling plants or even heating. So what's in kilowatt per ton? It's the amount of energy that you produce or you spend in order to produce a ton of refrigeration. Yes. Can I ask the students, where does this kilowatt go? What is a kilowatt per ton? Still. Electric energy, where does it go? Fine, that's the electric power that goes into the compressor. But then what does the compressor do? Ultimately it goes to, right. So a kilowatt per ton is the amount that I spend to transfer heat that is in the system, that is in the pipe, that is in this room, to transfer this heat that I have here and spend it out in the atmosphere. Ultimately, all the electric power that I put in and all the heat that I have in this room is going to the atmosphere. It's the amount of electric power or any other source of power. It could be burning fuel that I put in to turn this ton of refrigeration that I have, ton of heat that I have here in the room and put it outside into the atmosphere. Yes. Here when we talk about it, and because of our background into complete plants, we talk about the complete plant, this is the complete plant. I did mention Masdar, and this is why we went into the 0.5 kilowatt per ton. Again, if you go from here not too far to Riyadh, you will find systems that are much more efficient in Riyadh, even though it's hotter there. The reason for this is wet bulb and the way that cooling towers operate in high humidity or low humidity places. In Al Ain, we have a lower wet bulb, and you will find the total plant will reduce its kilowatt per ton marginally, but not a lot. Major components that you would see in a district cooling plant: we have mechanical systems like chillers, cooling towers, pumps. In pumps, we have different types of pumps. We have primary pumps, we have secondary pumps, cooling tower pumps. Again, you are the coordinator, yes? Okay. You finished your degree in engineering or something? Okay, fine. Let's find someone. What I want to talk to you about is not to restrict yourself to mechanical engineering or to petroleum engineering or to that type of engineering. Engineering is a sea that you need to swim in, and you will find all types of water in it. You will find the electrical water, and you will find the mechanical water, and you will find the civil water, and you will find the chemical water. don't restrict yourself to one stream of engineering and stick to it. Understand, analyze, and question. Why I say that? Even though mostly it's a mechanical plant room, but without the electrical switchgear that you have there, that plant can be a dead plant. You have high voltage switchgear that is there from electrical systems, transformers, low voltage switchgear, be it soft starters, VFDs. You have the control system there. Let me add to this. You have a chemical treatment for the cooling towers. You have footings and civil engineering that you need to do. You have monorails that you need to design, which is a static and a structural component. You have corrosion that you need to treat in the pipes. You have pressure and temperature that you need to understand. You have the cooling of that place that you need to analyze and find out that it's mostly heat and there is very little latent heat in it, mostly sensible heat and very little latent heat in it. All of those you need to understand them. No one is asking you to be the best electrical engineer when you are a mechanical engineer, but at least you need to know the basics of it and to be prepared to have the common sense of knowing whether someone is telling you truth or otherwise. The difference, again, I'm going to talk about the chillers and how we select them for a district cooling plant. The district cooling plant, in the end, a kilowatt is a kilowatt, whether you, well, not whether. Mostly, if you produce it in a building or if you produce it somewhere else, there is a certain kilowatts and there is a certain load. How do you go about it in district cooling? You minimize your flow and you increase your delta T. Where is our good mechanical engineer? There he is at the corner. What's the CP of water? Very good. This is what the number that I like to say. Well, that's the density, or no? That looks like a density, but it's not. The CP of water is the heat capacity of water. That is 4.187 watt. The kilogram Kelvin. Very good. What does it mean? What does it mean? Give me your definition. I don't want the Physics 101 definition. How much heat? Yes, it can carry. It can carry a lot of, it can carry 4.2, let's say 4.187 energy, not power, kilojoules in every kilogram. So let's look at 1 kilogram of water walking and carrying 4.2 kilojoules for every degree centigrade or degree Kelvin difference that it makes. So every time I increase or decrease the temperature of water 1 degree, I can spend or take from it 4.2 kilojoules. This is what we really... You should publish your diary one day. There might be lots of truth in it. We design our chillers on... Why I wanted this? Because I wanted you to know why we design for a large delta T. We want the water to carry as much kilowatts as possible. So we pump and we circulate less kilograms of water. It's kilojoules per kilogram Kelvin. So the less amount of kilograms that we circulate, it means the less pumping that we do. So we make this mule that we have, that is called 1 kilogram of water, carry more kilojoules for us than just one. If I circulate it on a delta T of 1, it means I can only carry 4.2 kilojoules in it. But if I make it carry 10 degrees Kelvin, this should be Kelvin, but for some reason these guys keep it on degrees C. You also understand that, yes? Okay. 10 degrees Kelvin in it, it means that I can carry almost 42 kilowatts of energy in 1 kilogram of water. That's a good amount. That's almost 42, that's 12 tons or something. We design what is called a GPM per ton. A GPM per ton is a degree of how much you can carry of water. These two numbers are related to each other because the CP of water is constant and is constant. Chillers in district cooling plants are vapor compression cycle. They use 134A, 123, or even ammonia. Yes. Gallons per minute, and it can be US gallons and it can be imperial gallons. This is the delta T. It should be in Kelvin because we're talking about the temperature difference. As a value, they are the same, but when you're talking about a delta T, because the degree C has a 0, so we cannot use it. We should use a Kelvin instead of the degree C. When it's a delta T, it's 10 degrees of difference. But when it's 10 degrees C, I have a 0. I can always go back to it. It's almost similar to enthalpy, whether it's absolute enthalpy or a degree of enthalpy. Do you want to define that for us? The amount, a degree C is a degree C, and a degree Kelvin, there is no degree Kelvin. A Kelvin is a Kelvin. It's the same amount, yes. But when we're talking about the difference, we talk about kelvins, and when we talk about a temperature itself, I say it's 25 degrees centigrade here. You have a reference of 0, which is almost 0.01 is the reference for melting of ice. Which university you go to? Because of the plant and the capacity of the plant, definitely we go to the biggest and the largest capacities that we have in the market. You can go up to 7,000 tons in a single chiller these days. Siemens have produced a 10,000 ton single machine. These are quite large machines. They could be from here up to the end of this hall. But generally we tend to use the 2,500 ton of pairs of refrigeration of chillers. Right? This is how it looks like if you meet it one day in the street. This is a centrifugal. Centrifugal chillers are more efficient and they have a higher capacity. Unfortunately, if the day that they produce a centrifugal ammonia chiller, I will be the first one to install them. You think R134A can be added to tea or chai? Every material is poisonous. Every material can harm you. Even water can harm you if it's used in the wrong way. Ammonia is a poisonous gas. So is 134A. So is R123. Each one of them has a certain degree of dangers that you need to mitigate and limit. But there is no problem in using ammonia. There's no problem in using any other refrigerant. Why I prefer ammonia? Because it's more efficient than any other refrigerant is there. It's fully natural. It's zero ODP. It's zero, what's the other one? Global warming potential, GWP. Okay. I'll talk about ODP only. Yes. This is a picture from a site under construction. You've got nice cranes that are building it. You've got multiple chillers that are being put in place. These are the plinths that you need to prepare for the chiller to come on site. Lots of preparation goes into this. You've got cooling towers that will take the heat that is in the return system and put it out in the atmosphere. This is what the cooling towers will do it. We should do another series on cooling towers because they are quite interesting machines. They cool the condenser water from, say, 42 to 33 degrees. Why do we choose the 33 degrees? Because it depends on the wet bulb temperature that we have. I mentioned Riyadh because Riyadh is quite a very low, very dry place, and hence the wet bulb in Riyadh is much lower. In Riyadh, the ASHRAE publishes the wet bulb that you need to use for Riyadh as 22 degrees C, where in Abu Dhabi it's around 30.56 or 87 Fahrenheit. 30.56, and these 10 degrees in wet bulb means a lot to the cooling tower, to the size of the cooling tower, and to the operation of the cooling tower. It also, because this is the water that you're returning to your chiller, it also means that your chiller will be condensing at, say, 5 degrees above this temperature. So your chiller condensing temperature is at 38 degrees. They have an architectural impact. Many people don't like to see cooling towers, even though they are beautiful. Pumps, from primary pumps, which if you do your calculations, and I'm sure you will go back today to the hotel to do your calculations on the district cooling plant, you will find it's around 420 to 500 liters per second. To be exact, on a 16-degree Fahrenheit chilled water plant, it will be around 473 liters per second. The pumps in a primary-secondary system is around 2.5 to 3 bar. A condenser pump has a higher range because it has to take the heat of the compressor as well up to the cooling towers. A total developed head of 3 to 3.5 bar. Can we do a test to the students, or we're not allowed? Can anyone tell me what's the kilowatts of this pump? Yes? You have the answer, but don't tell. Just roughly. Which is correct. This pump is generally around 160 to 180 kilowatts. We take our liters per second, we multiply it by our meters of head that we have, we multiply it by G, and then we should divide it by our efficiency to get our kilowatt. This is a nice picture of a pump. This is, I think, from a sewage plant. It's not from a chilled water plant. This is a pump, a condenser water pump. As you can see, it has no insulation because we don't insulate our condenser lines. It has a filter in front of it. This is the filter here that you can remove and take out any debris. You have flexible couplings there. You have a valve over there. And that's about it. Distribution pumps, these are the pumps that are responsible to take the water all the way through the network and bring it back to you into the plant. Because of the longer pipes, they are generally higher in kilowatts because there is more pressure to put into those pumps. Well, those pumps have to overcome a higher pressure in the network. Higher head, 6 to 8 bar is there. The quantity and the depends on the capacity and doesn't depend on the number of chillers that you have there. Remember, in designing or constructing any place and anything, the larger the machines, the less number of them means less headache for you, whether it's during construction or during operation of the plant. So generally, choosing a lower number of machines is better for you. And this is how a pump would look like because it's working on the chilled water system. It has to be insulated. Other components that you can put into the district cooling plant is thermal energy storage. Unfortunately, the plant that we're going to after some time, the plan for it was to have thermal energy storage, but we have to cut down on the capacity of installed chillers or the thermal storage tanks. Yep. You need secondary pumps and you need the thermal storage to provide backup. Thermal energy storage, we'll talk about it in a minute, about its operation or its, what for is it? It is for providing emergency chilled water. I never thought of them this way, but they are. When and inshallah we will have double tariff of power in this country, so we can start looking at saving some power. This is where thermal storage tanks can work for you by producing the chilled water at night and consuming it during the day. So we will not have the peaks of power that we experience here in Abu Dhabi or Dubai during the middle of the day. This is one way of using the thermal storage tank. There are other operational methods that you can use for thermal storage tanks. What can you store energy in? How can you store it? You can store it in water, which can store. How much can it store? How much water can store? With 10 degrees delta T, it will store 42 kilojoules. But this time we need to use energy, so we'll use kilowatt hour. Good. A storage tank employs stratification of water. What is stratification of water? It is putting two bodies of water in different densities on top of each other. We've all, as children, played with oil and water and tried to mix them, and they always sit on top of each other. And that's because of the difference in density between the two fluids. I'm sure in petroleum you have a different name for it, yes? Very good. Very good. You can use stratification as the deposition, okay, of fluid layers on top of each other due to difference in density. Okay. Here the difference in density, because we have the same material, we don't have oil and water on top of each other. We're not talking about an oil and gas separator. It is because of the temperature difference. So what we tend to do is we put water. We can put, yalla, we'll get to it in a minute. Okay. We'll put the cold water at the bottom and the warm or hot water on the top. Hot, what I mean by that is 14 degrees, 13 degrees, and the bottom will be around 4 degrees. If you pour them slowly into the tank, if you inject them slowly into the tank, you're supposed not to mix them, and they will stay unmixed on top of each other. Yes, the common question is there any plastic sheet in between? No, there is no plastic sheet in between. It's just two bodies of water sitting on top of each other. Given a very long time, yes, it will all come to 35 degrees, which is the ambient conditions. There is heat that will go from here out. There is a driver force of temperature difference between those two layers that will bring heat from the 14 degrees into the 4. This layer is called the thermocline, which is a layer that we try to control it within the range of half a meter, 300 mm. This is what we try to do. You cannot control it, but you try to design your diffusers in order to produce this very shallow thermocline. One thing, the higher the tank, the more you can store on top of each other, and the less the percentage of thermocline that you will have. So the more efficient your tank is. But at the same time, the higher the tank, the more pressure you will have at this edge, and the thicker the shell plate will be for you. So again, come outside your mechanical engineering or electrical engineering and think about structure and materials, and think about the thickness of this shell at the bottom of the tank, and that will cost you more money to build a higher tank than to build a short and wide tank. A short and wide tank means every 1 meter of thermocline is a lot more percentage of your volume and more inefficiency in your tank. This is how the temperature gradient would be. It would be 4 degrees from here all the way up to there. Then suddenly, within half a meter or 1 meter, the temperature will go up to 14 degrees and continue. This is a picture of a plant that we've constructed in Dubai. It's in Dubai Investments Park. This is a thermal storage tank, and that's the district cooling building next to it. The plant, this is a 30,000 ton-hour tank, which means it's around 11 million liters of water that is sitting inside. The height of the tank is 26 meters, and the diameter is around 23. Yes.
You keep adding chilled water to the bottom of the tank?
To charge it, yes. And when you need the chilled water from it, you need to take it. You take it from the bottom, and you put back into the tank. It's easier. it's the same medium that you are sending down to the user as compared to ice storage. You can store in ice. That's the question. How much can we store in ice, in every kilogram of ice? I don't have the exact answer, but it's a lot. 330 kilojoules compared to 4.2. So in every kilogram of ice, this solid pack of water, you can store 330 kilojoules. Yes? Yellow. The rest of the presentation is only pictures of installations that we have, and since we're going into a plant room, I don't think we need to go into details of it. The level of water inside the tank doesn't change. It remains the same. So whatever you're feeding in at the bottom, you're also taking up from the top. And vice versa, when you are spending the chilled water, you are feeding hot water to the top and taking chilled water from the bottom. Construction phases. Let's talk about construction phases. These are pictures that are taken from that plant, which is good because now you can see how it was constructed and what is the final finished product. Yeah, believe it or not, it was like this at one point in time. Chillers are delivered on site. Civil works is going on. Civil work is continuing. You've got piping and major piping that is running on each side of the plant. You need to do it all in one, depending on your program, but you need to work with different disciplines. This is still more piping going on here. Parts of the roof is being constructed. The roof is almost complete, and we've got the beginning of the cooling tower is happening here. The roof is added, and also the cooling tower is continuing. For some reason, we don't have pictures from in between, but we have the finished cooling towers. This is after painting, and all the civil works are done. Internal piping within the plant might be as clean as this, or it might be a very complicated piping system within the plant. Components that you can see here is cables, electrical cabling, piping. And these are drums of refrigerant that is being there. The control room is the heart of the plant, and this is the place that we need to operate. Let's go to the plant room. Questions, we'll talk about it later, or we'll talk after the plant room visit. Thank you. Did I?